Module 4 Discrete Time Markov Chain. Lecture 7 Reducible Markov Chain. The last 3 lectures we have discussed Irreducible Markov Chain, and this lecture we are going to discuss Reducible Markov Chain. So, in this lecture I am going to start with the concept of Reducible Markov Chain, then I am going to give the different types of Reducible Markov Chain, and also I am going to present some simple examples. Then finally, one important application of reducible Markov chain, that is a gambler's ruin chain problem. Gambler's ruin problem going to be discussed. Before we discuss the reducible Markov chain, let me explain the close communicating class of states. This definition we have already given in the few lectures earlier also. Again I am giving, using this we are going to conclude the Markov chain is a reducible Markov chain or irreducible Markov chain. The closed communicating class, suppose you collect the set of states that you name it label with a C. If that collection of or set of states is going to be called it as a closed communicating class of states, if it satisfies no such state outside C can be reached from any state in C, then C is said to be close communicating class of states. If in a set of states forming a close communicating class and it has only one element, only one state, you cannot include one more state, so that it is going to be a close communicating class of states, then that class is in that class the state is going to be called it as a observing state. And you know the definition of observing state, that means the one step transition probability I to I, that is equal to 1. So, there are two ways you can have a observing state, either Pia is equal to 1 or the close communicating class has only one element, then that state is going to be observing state. So, using a close communicating class of states, we are going to distinguish or we are going to make the reducible Markov chain and irreducible Markov chain. How? Let me see the definition of a irreducible Markov chain. If the Markov chain does not contain any other closed communicating class of states other than the state space S, then the Markov chain is called a irreducible Markov chain. Otherwise, it is a reducible Markov chain. That means you have a Markov chain with the state space capital S. You are trying to create the close communicating class. If that class and the state space S both are one and the same, that means all the states are going to form one closed communicating class. That means each state is communicating with each other state, and that is same as the state space, then that Markov chain is a irreducible Markov chain. Otherwise, that Markov chain is going to be called as a reducible Markov chain. Before we go to the various reducible Markov chain, I am going to give few examples. So, through this example we can make the classification over the reducible Markov chain. You see the first example, it has 5 states. Instead of the one step transition probability matrix, I have drawn the state transition diagram. So, using this you can easily able to conclude whether it is going to be a reducible Markov chain or irreducible Markov chain. If you see the arc from 3 to 1 and the states 0, 1 and 2, all 3 are connected, therefore, you can conclude 0, 1 and 2 is going to form a close communicating class, because all the states inside that class are communicating each other. There is no state going away from this collection to outside. It satisfies the close communicating class definition. Whereas the 3 and 4, even though there is a communication between 3 and 4 states, once the system goes from 3 to 1, it won't be back. Therefore, the states 3 and 4 are going to be transient states. The first visit, if you find out Fii, capital Fii for state 3 and 4, it is going to be less than 1. Whatever be the probability, here I have not assigned the probability. You can assign the probability positive 0 to 1, and you will get the conclusion the states 3 and 4 are going to be the transient states. So, since it satisfies the definition of a reducible Markov chain, that means you have a close communicating class which is other than the state space. That means you have a close communicating class with the fewer elements than the state space 0, 1 and 2 and a few transient states. Therefore, this Markov chain has a reducible Markov chain of some type. I am going to discuss later. See the second example. This also has the 5 states. If you observe, you will conclude the states 0, 1 and 2 are going to be the transient states, whereas the state 3 as well as 4 are going to form a two different close communicating class, but it consists of only one element in it, only one state in it. You cannot include the state 1 along with 3, or you cannot include the state 2 along with 4 to create a close communicating class. Therefore, the states 3 and 4 will form a close communicating class with one single state in each in it respectively, and these two states are observing states also. So, this is also going to form a reducible Markov chain. See the third example. This has 3 plus 3, 6 states. Out of 6 states, there is no backward arc to the states to the state 3. Therefore, state 3 will be a transient state, whereas states 0, 1 and 2 form a close communicating class. Similarly, the states 4 and 5 will form a another close communicating class of states. So, in the third example, we have two close communicating classes of states, whereas the first example you have one close communicating class and transient states. You see that all these three examples you have a collection of transient states and close communicating class, either one or many, or the close communicating class consists of only one element. But all the states, all the model has fewer transient states. Therefore, you can easily find out the reducible Markov chain whenever it is not going to form only one close communicating class with all the states. If that is not there, then all other things are going to be the and all other things are going to be a reducible Markov chain. So, based on these three examples, there are some more example I can create with the infinite state, but here I have not made it. But based on these three examples, you can have some idea how one can have a various types of reducible Markov chain. I am listing here. In these, the default is all the types has the few transient states. Along with that, it has a one close communicating class of states, that is a one type, one or more observing states, that is similar to the example 2. The first one is similar to the first example. The third one is with more than one closed communicating class of states, that is related to the third example. But here I have not specified whether it is a finite state or infinite state Markov chain. So, immaterial of that, the reducible Markov chain can be classified into these three in general. So, we are going to discuss out of these three, the first two we are going to discuss in detail, and the third I am not going to discuss. So, the way we are discussing the first model, the similar logic can be used to study the third type also. The first type, it is a reducible Markov chain. That means it has the fewer transient states and one close communicating class. My interest is to study the stationary distribution. Therefore, I am making further assumption so that I can go for studying the stationary distribution. For that, I am making the first assumption, it is a finite state model, state space is finite, and also this model state space has the one close communicating class and the set of transient states. So, whatever the states in the close communicating class, that state I am making at a aperiodic. Aperiodic is important to study the stationary distribution, therefore, I am making the aperiodicity. So, this state space is the collection of the transient states as well as one close communicating class. Therefore, I am making a two notation C and T. C for the set of close communicating class only one, the T is set of all transient states. Therefore, the state space S is going to be the C union capital T. Since it has one close communicating class and set of transient states, I am reordering the one step transition probability matrix such a way that the first few rows are corresponding to the states of the close communicating class. Therefore, I make it a C, but inside suppose the state space, the number of states in this reducible Markov chain is capital N, there is a possibility some fewer elements, fewer states may be in the capital C. Therefore, fewer rows, that will make a submatrix, that is P1. That means C to C, that submatrix is a one step transition probability submatrix is P1, whereas the one step transition probability going from close communicating class, that states to the transient states, that probability is 0. Therefore, all the entities are 0, therefore, this 0 is nothing but a matrix, submatrix, with the number of rows is number of states in the close communicating class, and the number of column, that is same as the number of transient states. This is the way we reorder the one step transition probability matrix. Therefore, C to capital T, that is the submatrix of zeros. The remaining elements are capital T, that you reorder it in the other remaining rows. Therefore, T to C will be a some non-zero fewer elements, that is a R1 matrix, R1 submatrix. And similarly, T to T, there is possibility of possibilities, therefore, the probabilities may be greater or equal to 0. Therefore, that matrix is a Q matrix. Therefore, the whole P matrix is divided partition into 4 submatrices, P1, 0 matrix, R1 and Q matrix. Since it is a 0 matrix, entries of zeros, therefore, this P1 is also going to be a stochastic matrix. The row sum is going to be 1 and the entities are greater or equal to 0, lies between 0 to 1. So, these values are, this submatrix will form a stochastic. This is called a stochastic submatrix. That means, I am just reordering this P matrix, that labeling the states such a way that first I am collecting all the states corresponding to the closed communicating class of states, then set of transient states, and this form is called the canonical form. For a reducible Markov chain, this canonical form is very important, because once you are able to make a canonical form, then you can study the stationary distribution in an easy way.